Hi, I'm Tom Stephenson, and welcome to Lecture 3B on framing. And in today's lecture, we're going to, in particular, look at floor framing using dimensional lumber. This is the second of 3 videos in this lecture, which is now going to be focused on dimensional lumber and floor framing. And we will have Lecture 3C, which will look at engineered lumber and floor framing. So let's get started. So we'll be looking at the structural elements that are involved in floor framing and help you to visualize the different materials, how they're placed, how they're used, some of the advantages, some of the disadvantages, and apply any OBC, Ontario Building Code, and NBC National Building Code requirements as they come up. So when we think about, some people will refer to it as rough framing. I'd say that's getting used less and less these days. They'll just say framing, but the rough idea is when we're using stick method, platform framing, like we discussed in the previous lecture, it's hidden when you're finished. So unlike timber frame construction where you'd want to see the exposed beams and posts, wood frame construction is hidden. One thing I didn't mention in the last lecture, I think that's worth talking about because we're talking about structural elements, is that stick framing, wood frame construction is a very resilient method of framing. It's very resilient to earthquakes, post and beam construction, timber frame construction, and it's more prone to problems. I remember I traveled to Japan in the 1990s, and I had to do a bunch of presentations for the Canadian consulate in Tokyo. And I think it was actually the embassy. But anyways, I had to do some presentations on wood frame construction. I had written some articles. It was very interesting at that time frame. The Kobe earthquake had hit, and there were subdivisions of houses, like just subdivisions of houses, just flattened. But every once in a while, there'd be a house that was standing on one block, on another block, and another block. And of course, they wanted to know, well, why is this house standing and all the other ones on the block flattened? And it was because those particular houses were built with wood frame construction, stick method or platform construction, as we like to say, with studs spaced at a certain spacing, joists, etc. And they were much more resistant to racking, the way that the construction process was done, whereas post and beam is not so resistant. So because you've just got posts and it just tends to collapse much more easily depending on how the post connections and beam connections were done. And of course, that went through all the newspapers in Japan, and then they started looking at Canadian construction methods. There was a lot of partnering with Canadian companies at the time. I remember at the time, Viceroy Homes, Canada was in the middle of a big recession during the early 1990s, and it was difficult for home builders from about 1990 to 96. But they were doing really well because they were shipping more houses, prefabricated houses in containers to Japan than they were actually building here at the time. So it is a very popular method of constructing homes, and in some places where there's seismic conditions, it can be, with a few adjustments, made to be really resilient during those cases. It's also why a lot of wood buildings today are being looked at very closely in areas that are seismic zones where earthquakes occur, like Seattle, like Vancouver, Christchurch, New Zealand. Most of their buildings were concrete, reinforced concrete, and then they had that dramatic earthquake there a few years back. They withstood the earthquake for the most part, so they were well designed. It's a very progressive country and all of those things. But then they were looking at, nobody really wanted to certify the buildings after the earthquake because it's hard to really look at reinforced concrete and determine the extent of damage that may have been occurred by the first earthquake. So they could design it that would survive a dramatic earthquake, but could it survive a second one, and who wants to take responsibility? So they're actually rebuilding, they rebuilt most of Christchurch using wood frame construction or engineered lumber like cross-laminated timbers, etc., as we'll talk about later in the course. So there is a lot of advantage to wood construction because if there is an earthquake, it's easier to identify where the problem is and fix it. And so that's a much easier thing to do remedially and less costly. So getting to rough framing, it's not visible, requires accuracy and insulation. So forget it. That's why I don't like the term rough. I use it, but I don't really like it because it's not rough. You want to be able to do it well. You want to be able to make sure the walls are plumb, they're laid out square. Footings and foundations that we talked about in the last lecture, very important. You've laid them out level, you've laid them out plumb, you've made them square. And you know what? If you did that and the tops of the foundation walls are nice and level, it's going to set a really good standard for your framing. If you mess that all up, then you're fudging everything. That means you fudge everything all the way through the project. It's not just the framing, it's not just the floors are out of level, you got to shim them up and try to level them off. Things that are out of square, you may not be able to square up. Floor tiles might go like this from one end to the other in the house, in the kitchen. Trying to get the cabinets level, a lot of extra work. Might never work, might never look exactly right. So you have to be very, in my mind, fussy about the layout and ensure that things are square, plumb, and level within minor tolerances. What's a minor tolerance? It's okay, 1/4 of an inch here or there. Depends on how long I'm talking about, but very minor tolerances. And I've seen some buildings that are new buildings that are quite unacceptable that way. It just makes the whole thing all the way through a struggle for all the trades. Okay, so we've got a foundation wall, and get used to looking at section details and plans. And if you have trouble visualizing it, you can go back into the chapter and go through chapters 2, 3, and 4 and get a better grasp of that. But a foundation wall looks like this. We have a sill plate that it goes on top of the foundation wall. We usually put a gasket. It's a foam gasket, and then we tighten this down to the actual foundation wall with an anchor bolt. The dashed line means it's hidden. It's in the concrete, embedded in the concrete. And that's your tie of the framing to the structure. And then you frame your floor joist on top. This we call a rim joist because it goes around the rim of the foundation wall. In this particular example, this would be assuming that we've got some sort of siding material going on the outside, an exterior sheathing and a siding material. This is not for a brick veneer, this example, but there are other ones, as you'll see, for brick veneer. So usually a 2x4 is used for the sill plate, and then we've got, it could be a 2x8, a 2x10, a 2x12 if we're using dimensional lumber, or it could be engineered lumber that we're using, as we'll talk about in video number 3. So the spacing, standard spacings are 12 inches, 24 inches, and the most common is 16 inches. And the reason the spacings are at that spacing is because they divide evenly into 8 feet and 4 feet. The sheet goods that we buy, like drywall, like plywood, comes in 4-foot by 8-foot sheets. Now, in Canada, we use the metric system, so our building code is 100% in metric. So the equivalent of 12 inches is 300 millimeters, 600 millimeters, and 400 millimeters if we're talking 16 inches on center. I say equivalent, but it's not exactly the same. Like that's just the conversion, then it's close, even conversion. So 300 millimeters, I think, is about 11 7/8 inches, something like that. The building code will just say 300 millimeters. Nobody lays it out at 300 millimeters. Everyone lays it out at 12 inches or 24 or 16. So I'm not going to lay it out at 400 millimeters, even though the building code says I'm going to lay it out at 16 inches. And the building code understands that the sheet goods is 4-foot by 8-foot, so it's not going to be a problem. If it says 400 millimeters, it means you can lay it out at 16. If it says 300, you can lay it out at 12, and so on. That saves us from cutting the sheets all the time because we can lay out the walls and lay out the floors so that the sheets will fall and be even on that space. You just have to cut them on the ends, wherever the end of the floor is or wherever the end of the wall is. So that standardizes it, and also standardizes it for strength. So all the engineering calculations in part 9 of the building code, it's pre-engineered. All of the tables that you'll see in the building code for spans for joists, it's pre-engineered and designed, are assuming either 12 inches, 16 inches, 24 inches. Another one that's become popular, more popular for walls, is 19.2. 19.2 doesn't divide evenly into 4 feet, but 19.2 does divide evenly into 8 feet. So if you go 5 times 19.2, that's 96 inches. So it does divide evenly into that. And even a tape measure will have a little triangle on it that'll show you where 19.2 measurements are. If you go to chapter 2, you'll see a little image in chapter 2 that shows a tape measure and where basically the images are on that. So that is our floor framing and our floor spacing. And it's designed based on how far is the lumber spanning. Span is from support to support. That's our clear span from the edge of support to edge of support. The longer it's spanning, the thicker our lumber, or the wider our lumber has to be. 2 by 8, 2 by 10, 2 by 12. The wider the span, the wider it has to be. The closer we have them together, we might get away with using a 2 by 10 instead of a 2 by 12. So, or if we're putting ceramic tile on the floor, you might decide that it's much better to use 12-inch spacing because there'll be less deflection in the subfloor. That way the ceramic tile won't crack. So these factors that determine the spacing for walls and floors. Walls sometimes, well, I'll leave this till we get to the wall discussion, the 19.2 where it comes in, which is in the next lecture. So all of these points on center spacing. So that means from the center of joist to center of joist is 12 inches. Well, that's the same as saying from this edge of the joist to this edge of the joist is 12 inches. From that edge of the joist to that edge of the joist is 12 inches. But we usually say OC as an abbreviation on drawings, on center. So the goal is to be able to lay down the subfloor, install drywall with as few cuts as possible, and to be able also to lap them to strengthen the floor overall. So usually when somebody starts from one side, they'll start with 15 1/4, so the middle of the sheet will end up in the middle of the joist. Kind of looking like on-center spacing in this way, if we had to go for 96 inches, like the length of a sheet, you would have essentially 8 spaces here if we're going with 12 inches on center. If we're going with 16 inches on center, we would have 1, 2, 3, 4, 5, 6 spaces, right? And 19.2, we'd have 5 spaces, and 2 feet, we'd have 4 spaces. So you get the idea. Obviously, this would be a little bit of a problem going 24 inches with a subfloor. We would have to have a dramatically thicker subfloor than we would here because of the deflection rates. I have seen as much as 32 inches on a span, and it was in using engineered joist, and it was for a prefab condominium building that was being built. I think it was Mattamy Homes, and they had a special engineered subfloor, and I think it was about 1 3/8 inches thick that would span that distance. Usually we use 5/8 tongue and groove for subfloors. That's the most common, or 3/4 inch tongue and groove for subfloors. So when we're using 16 inches, 12 inches. So here, this is the minimum bearing according to the National Building Code and the Ontario Building Code, 1.5 inches. So when we say bearing, it's just how much is this sitting on a support. If I say bearing for a beam or bearing for a joist, that's what I'm referring to. So that's 1.5 inches. You'll find the same bearing for like a roof rafter on a wall, 1.5 inches. All right. So that's the minimum bearing, unless you're using joist hangers, etc. So we have joists. We also have beams, and dimensional lumber is limited by its strength. That's probably the Achilles heel of dimensional lumber. It's limited span by strength. It's also other Achilles heel is shrinkage. So when we talk about engineered lumber, you'll see some of the advantages there. So we use beams to help us be able to open up things to wider distances. So beams help us to do that. And usually we can use with beams steel, built-up wood beams, engineered beams that would be following in the last two categories. Very common is steel and built-up wood beams. Steel is very preferable in wood frame construction if it's right through the middle of a house going from one end to the other. Built-up wood beams are not bad for shorter spans that we want to have the joists run into each other that way. Much easier to install. So usually what determines it is ease of placement. How are we going to situate the beam? Is it going to be, the joist going into the sides of the beam? Are they going to be underneath the beam and then the beam is on top? The types of materials that we're using. If we're using steel beams, we have to have a minimum bearing of 89 millimeters or 3.5 inches. So for steel beams, that's the minimum building code requirements. Could be more, depending on what the drawings say, but it won't be less. The end bearing varies depending, when we talk about built-up wood beams, depending on the span and what they call the supported joist length or the supported length as the building codes require, NBC and OBC. A supported length is, well, I got a beam going this way. How much of the joist is resting on it? So is the joist that's resting on this beam 16 foot? Well, that would mean it's resting, the joist going from the beam to an outside wall. So if it's 16 foot, then 8 foot of that joist is resting on this beam. Because the other 8 foot, the weight is being distributed to the other wall. This 8 foot's coming to the beam. Now maybe on this side I've got 10 feet of joist to the wall. Well, then 5 feet is resting on the actual beam and 5 feet is going to the other wall. So this beam would be carrying a supported length of 5 feet plus 8 feet, half of the spans on each side. So then that would have a supported length or a supported joist length of 13 feet. Then the other thing that has to go into consideration is how many floors is it supporting? Is it a 2-story house? Is it a 3-story house? So if it's in the basement, then that beam is carrying the weight of the first floor and maybe there's a load-bearing wall on top of that. So now that beam is also carrying the weight from the second floor and the first floor. So again, it's going to have to be designed to be strong enough to carry the weight of both floors and so on. So there are tables in the building code that require that the minimum bearing for built-up wood beams, and this is just giving sort of a building code sort of outline of it. 3-ply beams means you got 3 joists side by side that are nailed together that make up that beam. So 3 pieces, that would be 3-ply. 4 pieces, that would be 4-ply. 5 pieces, that would be 5-ply. And in the book, it's got some good examples that you can sort of read through, but 3-ply beams that support more than one floor with a supported length. How much is the length? And of course, it's going to be all in metric because it's the building code. 4.2 meters require 114 millimeters bearing. So that's how much has to sit on each end of the wall. All other beams supporting not more than one floor require 76. Where do they get these crazy numbers, 114 and 76? Well, if you remember from the last lecture, we talked about dimensional lumber, and we said like 38 millimeters by 184. That would be a 2x8. All the dimensional lumber was 38 millimeters thick. That's standard. So 38 millimeters twice is 76. 38 millimeters 3 times is 114. So it's saying, if this beam is going across here, I would have to have 3 members supporting it. Maybe it's 3 2x4s or 3 2x6s. So 38 plus 38 plus 38. That would be holding up that beam at least. So that's where they come up with those numbers. So beams not supporting more than 3 floors and beams not supporting more than 2 floors and 3 floors. So you can sort of see it gets more bearing because it's carrying more weight because it's carrying more floors. So you can sort of just follow that through without me just going through it individually, and read it through carefully in the textbook, and that will help bring that to bear, that understanding. So when we talk about beams and we talk about stress points, when you've got a floor resting on top of it, well, what we've got here is we've got this sort of situation where we've got a load coming down on top of something, and when it pushes down, right? As I push down on this, you've got basically you've got compression on the top and tension on the bottom. So here in this image here, as the weight comes down on this beam, the bottom is under tension and the top is under compression. It's also why you can't notch. They don't even allow you in the building code to drill through a built-up wood beam. So you have to be careful of notching and drilling requirements. I'll cover that in the lecture that we do on the subtrades. They tend to like to drill through things. So you have a load coming down. It puts the top under compression, the bottom under tension. The middle is considered neutral. All right, the middle is considered neutral overall. Same thing with the joist. They work the same way. On a long span with a joist, the bottom's going to be under tension, the top's going to be under compression. And of course, there's a shear force, like a cutting force, that happens right near where the support of these items are. Okay, so there's a shear force that comes into play there. And if we didn't have enough bearing, if this was a very small bearing, then the amount of weight, it's not being distributed over there. That could cause more problems in your structural integrity of the building. So that's why we have minimum bearing for a joist, 1.5 inches or 38 millimeters. Minimum bearing for a steel beam, as an example, 89 millimeters or 3.5 inches. And like those varying requirements that we just talked about with lumber. It's good to understand these forces. Also, when you talk about concrete, reinforced concrete, it's good to understand too. So here, like on a set of drawings, it might say like 338 by 184, SP number 2. Now that I'm thinking about it, SP, I don't think I mentioned in the previous lecture, from the grading stamp, it says SPF on the grading stamp. That stands for spruce, pine, fir. On the drawings, if you see SP, that refers to spruce. That's the species of lumber, and the different species, the building code has identified, tested, and then categorized based on their strength. So very typical lumber that when we talk about dimensional lumber, you go to Home Depot or your local lumber supplier, this is what you're going to typically find in Ontario anyway. Some lumber yards out west, you may find Douglas fir, etc. But in Ontario, SPF, that's the most common. This is the grade of the lumber, number 2. So that's what you have to make sure that you at least meet. You could use number 1, that wouldn't be a problem, but you couldn't use number 3. And this is saying 338 by 184 put side by side, right? And in this case, it's saying that they're going to be flush. So that means this beam, when the house is finished, you won't know it's there because it'll be flush with the joist. The joist will go into the sides on hangers and be supported on hangers that way. So kind of shows you, here's an image here. This is a built-up wood beam, and there's 1, 2, 3, 4 plies. 1, 2, 3, 4 plies. And you see this little strip here? Remember when we talked about the grading of lumber? Well, that one made it through. Always with lumber, some of them make it through, but not too many. This would be a number 2 grade, but it has wane. That wane is like a little bit of where bark was on the side. So this was very close to the outside of the log. And of course, that does weaken that piece. But overall, there's enough factor of safety in there that would be okay. In this case, they've actually doubled the joist. By doubling the joist, they were able to expand the span a little bit. Doubling the joist is not a standard item in Part 9. It would have had been engineered under Part 3. So an engineer would have designed that aspect to get the little bit extra. And I think on this particular production site, they just wanted to they've used pretty much 2x8s everywhere. So rather than, because this is a little bit longer, go to a 2x10 and have to adjust things, it was easier for them, even though it was a little bit more expensive to double them up, to do that. There could be a variety of reasons why these things take place. And this is what we call a solid bridging. So it's solid lumber that's going in between the joists, and it really strengthens the floor from deflection when you actually walk on it from up above. Here we have a beam that's a steel beam, and you've got joists, and you notice the joists are notched on the top. You can notch joists on the top, but there's limits, all right? So there's limits that you can do. And then, so they notched it on the top and they put a filler piece across, nailed it to the side, and so that the subfloor would be supported. That's the hatching, and that's a subfloor up above. And you notice they left a space there. Well, we spent a fair bit of time in the lecture 3A talking about shrinkage. Well, you know what? Some conscientious carpenters, sometimes they'll cut the piece and they'll make it exactly fit there so it's really strong there, and it's like, I'm doing a great job. They just caused a problem, because when this lumber joist shrinks and this lumber joist shrinks, it could, if this was tight here, what's going to happen when that pulls down? It's going to leave a hump up there. It'll leave a hump in the floor. And what if you had ceramic tile? I've seen this a number of times on top of there. The ceramic tile will crack right along there. So this conscientious carpenter actually caused a big, expensive problem in the floor, because then usually you can't match the ceramic tile. You got to get another ceramic tile, and you got to do the whole floor in that section, and it's not nice. So what you want to make sure is that you leave a space around here and a space around here so that there's no shrinkage issues, that if it does shrink down, it won't have this pushing upward on that. So when we talk about beams, they will be found on drawings, and they'll be designed from the building code to be a certain size. So if you look in the building code for a beam, standard beams, it'll say like W200 by 33. The W stands for wide flange I-beam. So it's just a typical I-beam. They call it a wide flange I-beam. The flange is a certain pre-described width. 200 by 200, that's the beam height, 200 millimeters. And then the 33 is the weight, 33 kilograms per meter. It's the weight per kilogram per meter. Here, this would be an imperial. That one's in metric. This one's an imperial. You're going to know right away it's imperial because it would say W6, W8, W10, W12. So it's not going to, you're not going to have an 8 millimeter thick beam like high beam. So W8, wide flange I-beam again, and it's 8 inches high, 15 pounds per foot. All right, 15 pounds per foot. So if it's 10 feet long, I know it would weigh 150 pounds. So I can right away tell how much it's going to weigh. The other thing that you can tell too is you could have a W200, say by, I'd have to look at the exact weights, but let's say it's 25. Then I would know that the 25 isn't as strong as the 33, because it means it's not as heavy. So it means the steel isn't as thick. So you're going to design it based on what the supported length of the joists are, what the span of the beam is between the columns, and how many floors it's supporting. So it's got to be carrying the supported length of the joists, what's the span between the columns, and how many floors is it supporting when we're talking about beam design. And there's a bunch of predefined tables in the building code that can be looked at that give you those dimensions and sizes pretty easily to tell you what standard beam size you could use. If you want to go customizing in extra spans that are beyond Part 9, then you hire an engineer and they will do the calculations based on Part 3 of the building code and provide a beam size for you. So here on this little drawing clip, this is what it would look like. You see this little dot, that's for the post that would support a beam. This dashed line around it is for the column footing. And this is basically a W200 by 27 beam. It would sit in a beam pocket. This number is 16. I could look at the construction notes on the first page and it would tell me what that is. So a beam pocket, basically a built-up wood beam or a steel beam goes into the pocket. If it's a built-up wood beam, you should leave a space around it. Usually they'll put plastic around this and leave an air space so that air can circulate around so it doesn't get moist and damp and it can dry out. If it's a steel beam, it just gets packed in with a concrete mix like this around it. So you got the steel beam, then the joists are resting on top of the steel beam. In this case, they're resting on top of the steel beam, and this strap here is nailed to the underside to hold the joists at the right distance apart, if it's 16 inches on center or 12 inches on center, etc. In this case, you've got a wood column that's supporting a steel beam. So the wood column rests underneath the steel beam. The weight comes down from the floor above. That weight, part of the weight is going this way, part of the weight is going that way, and this would be the span of the beam. And before, when I was saying, you know, the supported length, well, how far do these joists go to the other beam or the other wall, and it would be half that distance would be the supported length. So if it went 16 feet this way, so 16 feet out that way, then 8 foot would be supported on this side. And if it went 10 feet from here to the outside wall there, then 5 feet. So that's the 8 and the 5 I was talking about. This is covered around with plastic. It's resting on the footing. Wood columns can support steel beams as long as the steel beams are not carrying bricks or masonry construction. And this plastic is wrapped around because the concrete floor is going to be poured over top of this and on top of the footing. But the post should come down to the footing, not on top of the concrete slab, because then the slab will probably crack. Here's a steel beam, and it's got basically ledgers that have been bolted between both sides. And then these joists are on what we call joist hangers. So every nail hole in the joist hangers has to be filled with nails, and that holds these joists in place. In that case, you don't have to have the joist bare 1.5 inches because these metal joist hangers are designed to carry that weight. And then this is just held down a little bit lower than the steel, and then the drywall would go right across, and you would never know that there was a beam in place after construction. This would be where the drawings would say flush when it's finished. So this is conversely, so that's where it's flush. Conversely, this is where the joists go over top. Generally, this is the way you'd like to do it because it's much easier to run ductwork and piping through. How do you run ductwork and piping through here? You're going to have to lower it below the ceiling, and then if it's in the basement, that would be kind of a bother. If it's on the first floor, then you probably have to have some bulkheads to hide the ductwork. Bulkhead is a little drop box. So they lap over side to side. That's the quickest way. You don't want the joist to run too far past the support, right? So within about 2 or 3 inches, you want to stop them. Some framers, again, they just run them long because they, you could have a joist that's 10 foot 2 and you run it long, and because it's a 12 footer, you had to buy a 12 footer. It's way out here. Well, when this pushes down, remember there was that drawing we had where the beam goes down and it's under compression on the top and tension on the bottom. Well, when that goes down, what do you think happens to the outside edge if it's way out here? It actually goes up, and that would push up on your subfloor. Again, if you had a ceramic floor, that could cause cracking and problems. Here's the ledger strips, but remember, you would want to keep a space underneath this ledger strip because if this shrinks and that shrinks, that could cause a problem. So you're always thinking about your construction details and how shrinkage might occur. I would want to make sure I've got a 1/2 inch space underneath here so that I don't have problems with shrinkage. Same here. So don't forget that. Just because it doesn't say that, that doesn't mean you don't do it. This is a point load. I think I mentioned in the other video if you had a load from, say, a column up above or something coming down, you want to make sure it's transferring that load down to the beam. If you don't, then that load is right there. Then that subfloor, it'll start to sag. It could even shear through if it was enough of a load, but more likely it'll sag, causing cracks in your ceiling, maybe making a door stick because of movement across the lintel of the door. So you put point loads to make sure that the loads are being transferred effectively to their bearing supports going along the steel beam and then down the columns to the footings. And when we lay down the subfloor using dimensional lumber, we should stagger it. It doesn't matter, dimensional lumber, engineered lumber, we always stagger it. Same with drywall, we stagger it because if we have one straight joint going all the way around long, it's not as strong as this is lapping over it. And when we screw down or nail down the subfloor, it dramatically strengthens it where every second sheet bridges over. And our subflooring material is always made for our plywood or OSB. OSB, it kind of looks like, maybe there's an undershot here. See all that sort of flake board? That's what we call OSB or wafer board, oriented strand board. It's all these little chips of wood that are glued and oriented a certain way to provide the effective strength. And it's designed to go perpendicular to the joist. So the long way goes perpendicular across the joist. So you can see the OSB everywhere. Plywood's a little bit more expensive, so you usually see OSB in production homes. Usually in custom homes, you'll see plywood. It's a little bit more durable, a little bit better. If it's protected from moisture, they're all pretty good, but plywood's a little bit more resilient when it comes to being protected from moisture. This is what we call cross bridging. Stops the bounce in the floor, strengthens it. Building code requirements that any spans more than 2.1 meters, you put in bridging. And this is cross bridging. This is usually preferred over solid bridging just because it's easier for the electricians to run pipes and plumbing around. This makes it much stronger, the floor, like a little bit more tighter. And this is an engineered bridging, which actually you can, if you're getting the floor system to try to run a little bit longer and you get an engineer to review it and stamp it, then that would generally give you a little bit extra distance that perhaps you could get away with a 2x8 instead of going to a 2x10 or 2x10 to a 2x12. Some of the different framing details that you can use between the joists and the beams, that you can typically use. I wouldn't advise for this because it's notched on the bottom. I wouldn't pass that with the building code myself, but it's there nevertheless. You're not supposed to notch on the bottom anywhere. You can notch on the top, but not on the bottom. Like this would be okay. You'd be better to cut that off, and put a piece scab to the sides. And this is on a hanger, as I was mentioning. So different methodologies and different ways of joining up. There's quite a few different methodologies you can use. This is a floor opening. So remember this. This is a header, right? And this is trimmers. So trimmers support headers. That's how you know the difference. Trimmers support headers. Headers support joists. And these would be called tail joists, these shortened joists. And this would be a double header. All right, and this would be a double trimmer. So if I was to ask what's supporting the most weight, well, I would suggest to you that the trimmers are supporting the most weight because they're supporting the headers and the joists, as well as their own weight. So you'll find that you have to triple these up before you have to triple these up under the building code requirements. It would tell you on the drawings whether they're double or triple. You usually say TJ or DJ. DJ double joist, TJ triple joist. Here we have the floor is cantilevered. So when a floor goes out, it's considered cantilevered. And if we're following part 9 of the building code, you can go out, you have to go back 6 times the distance that you go out. So that's that cantilevering effect. And you have the limitation of going out, I'm going by memory here, 2 feet. If not, if you want to go out more, again, you can do it. You just got to get it engineered and designed. And don't take me for granted on the 2 feet. I'd have to double check that, but I guess 2x10s, 2 feet, 2x8, 16 inches, but I have to double check. So here's an example on the drawings from your textbook, the Doncaster house. This is being cantilevered out. And so you see how far back, and that's why it says double joist cant, triple joist, double joist cant. And that's pushing this to a box window that sticks outside. So the box window is this window on the outside that sticks out. This is what it looks like on the inside. This is what the detail looks like. And this is the joists that are sticking out this way, and they're tripled up. So you're always trying to visualize how these framing members are going together from the drawings to the actual construction of a residential structure. So it's really worthwhile to spend a lot of time trying to interpret and understand drawings. So here this is the triple joist, 3 plies. So remember I said how many plies? 3 plies, triple joist, same thing. All right. And the joists are going out and they're cantilevered out past here. There's the double joist on the end. And you can see that they're on hangers. So it's flush, right? So the whole floor system is flush. And looking at it in a BIM drawing, you can see the steel beams down below. You can see the columns going down, and you can see the joists are cantilevered out past, and you can sort of see the whole layout. So that's looking from you're kind of looking at this, and you're looking at this. This is your orthographic drawings, one view at a time, detailed drawing. This is actual construction and how it would be constructed. And I think this gives you a pretty good 3-dimensional view of that process. And you can see the sill plate underneath that it's resting on. So piece by piece, starting to visualize what's going on. It's important. And here's subpanel orientation, again, the lapping over that I talked about. Headers, trimmers, tail joists, regular joists. I mentioned the building code has a span table. So the span table is here. They have a number of predefined tables. I may not have said span table. They have beam tables, span tables for floor joists. So we talked about the strength of lumber, spruce, pine, fir, right? So what's the commercial designation from the grading stamp? Remember, grading stamp, that was from lecture 3A. If you didn't see it, go back and watch it, read the chapter, and that'll make sense to you. So spruce, pine, fir, and it tells you all the individual species of fir. Ontario, it's this because that's what we have predominantly available that we cut, and it's least expensive. You'll see in the building code there's a whole bunch of different tables for different wood. Maybe different parts of Canada you'll find different ones more common, but spruce is pretty common, SPF, and they call it SPF, but on the drawing they might only just say SP. Maybe I got an example of that going back here. Let's see. See how it says SP, spruce. There you go, spruce. Okay, and then I said the grade, and I said number 2. Most of the stuff you go in a lumber yard's number 2. Some lumber yards, they carry number 1. As far as the strength goes, it's all in the same category, number 2 or number 1. Number 3 is different, right? And so if I had a particular span that I was looking at, say I was looking at a span of maybe 3.8, right? I might then look at my table, and then this is with strapping and bridging, this particular one. When you have strapping and bridging, it can go a little bit further. Let's see here. So strapping, you see that strap there? That's strapping and bridging. There's your bridging, there's a strap. You're only going to really use strapping like in a basement condition, right? And if you finish the basement, then you just finish the strapping in the basement across so you could screw your drywall to it. But that gives you more strength for the spans of the floor. Probably the drywall will be strong enough with it. So that's using strapping and bridging. This is the spacing. So that's 12 inches, 16 inches, 2 feet. 300 millimeters, 400 millimeters, 600. That's the spacing you're going to put the joist at. So if I had 3.8, I can't go with 16 inches because it won't span enough. This has to be more than whatever I want to span. If I've got a 3.8 meter span, this will work. So if I keep it at 3.8 meters, then that would tell me I could use 2x8 joists, 38 by 184. This is a 2x4, this is a 2x6, this is a 2x8, 2x10, 2x12. That's all you can remember. Instead of remembering each size, you can remember 2x4, 2x6, 2x8, 2x10, 2x12. And that would be the species, and that would be the grade. That's how the numbers are arrived at. Sometimes you could decide choices. Let's see, I might have to put my glasses on for this one to see it. I got the line kind of in the way. I think this says 3.81, the line's crossing it, but if it was 3.81 and I had 3.8, technically I could do without the strapping, right? Technically I could do without the strapping. Probably wouldn't want to cut it that close. Remember, the building code is the minimum standard that is legal. Anything beyond that's illegal. So when you cut it really tight, it's okay, but it might deflect, you might feel a little bit more bounce in it, that sort of thing. So that kind of gives you a good sort of heads up on dimensional lumber and how dimensional lumber is used for floor framing. In the next lecture, we're going to look at some of the aspects of engineered floor framing. And I'll give a link that'll give you some opportunities to watch some of the videos at one of the the truss joist manufacturers. Okay, so I hope that's given you some good insight into the framing process. You do want to be very cognizant of what the drawings tell you. Sometimes the drawings will tell you in one little spot, everywhere there's ceramic tile, 12 inches on center. If that's the case, you got to be very careful of looking at the drawings, because sometimes drawings can counter each other. In one spot it might say this spacing is 16 inches, but then it says over here, wherever there's ceramic tile, do it at 12. Well, you should do it at 12 where the ceramic tile is. Less deflection, less warranty issues, less problems. Be very cognizant of reading the drawings and the specifications very carefully and closely so that you don't miss anything. And better to have it more structurally sound than less structurally sound, because rework is not fun. do it right the first time. As the saying goes, what is it? Measure twice, cut once. Okay? So I'm Tom Stephenson, signing off for now, and we'll see you next time for Lecture 3A. Bye for now and have a wonderful day.